So we'll continue our discussion with the next type, which is the JK flip-flop. Okay. So here, in the previous case, which is the SR flip-flop, we discussed the not used case when J is equal to 1, when S is equal to 1 and R is equal to 1. When clock is high, when clock is high and S is equal to 1, R is equal to 1, we cannot determine what will be the output. So always the output will change to 0, 1 like that. Always the output will be 1, 1. 1, 1. So we cannot say that this is a stable case. This is an unpredictable state and this we are not expecting in the output. Okay, so this is an unused state. So in order to overcome this particular problem in the SR flip-flop, they have designed a new circuitry and almost all the internal connections are same as that of SR flip-flop with a small change. So I will draw the diagram for that. So this is our SR flip-flop. So this is Q and this is Q bar and this is S, this is R and we are having a common clock. Okay, so this was the SR circuitry. So, so the design of this particular circuitry has been changed a little bit and what they have done is this Q bar output, this Q bar output is given as the input of this particular gate. Okay, so this particular output is fed back to as given as a feedback to the input of this gate. So this particular gate becomes a 3-input AND gate. Similarly, the output Q is taken and it is given as the third input of this gate. Third input of this gate. So in the previous case, we had only 2 inputs in this case, but now we have added one more thing. Now we will see how this will work. Okay, how this particular case will work. So in the previous case, we know when clock is equal to 0, clock SR. Okay, so these were the cases. So what is the output Q and Q bar? We know. Q and Q bar we know. So when clock is equal to 0, S and R, whatever be the value of S and R, the output will remain or it is a memory state. And if it is 1, 0, 0 also it is memory. Okay. If it is 1, 0, 1, then Q is equal to 0, Q bar is equal to 1. If it is 1, 1, 0, then Q is equal to 1, Q bar is equal to 0. And these cases are same for this also. For this particular circuitry also, these cases will work similarly. But we have to check for the last case where clock is equal to 1, J is equal to 1 and K equal to 1. Okay, so this is the condition that we want to check here. What happens when clock is equal to 1, S is equal to 1 and R is equal to 1. Okay, now we will take that particular case. So here we are assuming that S is equal to 1. And assuming that S is equal to 1 and we know that clock is high, always high. So R is also 1. Okay, so we know these two inputs to the system. And here in the output we can have two different cases. We can have Q equal to 0 and Q bar equal to 1. One case can happen and the other case is Q is equal to 1 and Q bar equal to 0. Okay, these are. So let us assume that the previous output is Q is equal to, when S and R is equal to 1, assume that Q is equal to 0 and Q bar is equal to 1. Q is equal to 0 means that output I am giving back to this particular gate. So this input will be 0. When q bar is equal to 1, that I am giving to this input of this gate. So this is equal to 1. Okay. So what happens when this input is 1? 3 inputs are 1. 3 inputs are 1 means the output of this will be 0. If one input is 0, output of this will be 1. So for a particular latch, so this is a latch, right? When we are adding this part, it becomes a flip flop. This part is a latch. So this is an SR latch. So what is the output of SR latch when input is S is equal to 0 and R is equal to 1? When S is equal to 0, Q is equal to 1. When and Q bar is equal to 0. Okay, Q is equal to 1 and Q bar is equal to 0. Now what is the next step? The next step what will happen? Assume that this is 1 and this is 0. So I am giving back this input to here. So this 0 becomes 1 and this 0 I will give to this input. So this becomes 0. So what happens, this input is 0 and this input is 1. All the three inputs of this gate is 1. So output will be 0. Or one input of this particular gate is 0. So I will get output as 1. So for this particular latch, this is a latch portion. So in this latch, if this input is 1 and this input is 0, I will get output as 0 and this output as 1. See, this is 0 and this is 1. So I am again giving back this 0 to this gate. So this becomes 0 and this 1 I give back to this node. So this becomes 1. So these three inputs are 1. So output will be 0. This one input is 0. So this output becomes 1. So when this is 0, this is 1, what is output of this latch? This is 1 and this is 0. Again what happens? This 1 I will give back here. Instead of 0, I will get 1 here. This 0 I will give back to this particular node. So this input becomes 0. So output of this particular gate becomes 1. Output of this gate becomes 0. So 1, 0, input of this latch will give you output 0, 1. So from this what you can understand? What you understood from this particular implementation? If I am giving a feedback like this, the output you can see a frequent change in the output, right? So output initially it becomes 1, then it becomes 0, then it becomes 1, then it becomes 0, so it will go like that. So it will repeatedly go like that in an infinite way. Oh, so this is an uncontrollable output. Whenever we are giving such a feedback, the output will go on changing from 1 to 0 and 0 to 1, and that is known as toggling. Changing of output from one state to another is known as toggling. So output will toggle from one state to another. So from 1 to 0, 0 to 1, 1 to 0, 0 to 1, like that it will continue. So whenever we are connecting such a feedback and if both S and R inputs are 1, 1, this particular output will keep on repeating or keep on toggling uncontrollably. So this uncontrollable change in the output is known as racing. Racing. Uncontrollable output. When both S and R is equal to 1 in this particular condition, when these inputs are 1, if I am giving such a feedback system, then the output will go on changing uncontrollably. So this is a case where this particular case is known as racing. Okay, so when S is equal to 1, S is equal to 1 and R is equal to 1, we will say that this particular case is a toggle case. Toggle case. And this particular system condition is known as race around condition. This is a very important portion for your exam. They may ask you to explain what is a race around condition in this flip-flop. Okay. So here, when you are giving such a feedback, this particular input is renamed as, this is renamed as J and this is renamed as K. So when this particular feedback system is given, this particular system is known as a J, input is having J and K. So this flip-flop is known as JK flip-flop. So in your exams you may ask you to explain the raise around condition in JK flip-flop. So in that what you can explain, you have to explain what is the output in each of the cases, and in the last case when clock is equal to 1 and S and R, instead of this S and R you can write it as J and K. So when J and K inputs are 1, 1, then the output will keep on changing uncontrollably. So it becomes 1, then it becomes 0, again 1, 0. So it will toggle uncontrollably, and that particular state is known as a toggle state, and that particular mechanism is known as raising. And when you are saying that when J is equal to 1, K equal to 1, that is called the raise around condition. Raise around condition in JK flip-flop. Okay, so this is all about this JK flip-flop. So we have discussed what is a JK. Okay, now so this particular output can say that if I am taking what is the next state of the system, when clock is equal to 0, if both are XX, the previous state will remain in the system. Whatever be the previous state, whatever Q1 is there, it will remain. When clock is equal to 1, both J and K are 0, 0, the output will remain. In that case also output will remain. When J equal to 0, K equal to 1, output is 0. When J equal to 1, K equal to 0, output is 1. When both Q and J and K are 1, 1, whatever be the previous output, you will get the complement of that. So that is Q and bar. So this particular case is known as the raise around condition or toggle state, or it is also known as raising. Okay, so this is the table for JK flip flop. And in case of So this is a case of JK flip-flop. And now we will see this master slave flip-flop. So here, in case of JK flip-flop, I will just give you one simple example why we are going for master slave. So here, you can say that assume that a clock is high. Okay, assume that clock is high. So this is our clock. This is the clock. Okay, so assume that when the clock is high, this particular function, this particular thing will or particular circuitry will get enabled. And in case of this 1 1, when you are giving both J and K as 1 1, if I am giving a particular clock, and even though as long as the clock is high, the output will continue to toggle within that clock itself. So this is the condition that I want to explain. This is the clock. This is the clock. This is 0 to 1. And here, when the clock is high, what will happen in this case of JK flip-flop? Within the clock, as long as the clock is high, this particular system or particular output will toggle. So it may toggle a number of times. It may toggle, it may go from 0 to high, it may go from 0 to high like that. When clock becomes 0, again it will go to the previous state. Then again when the clock becomes high, again it will start toggling. It will start toggling. Okay, so this is the case of, this is the particular problem with this, this is known as a racing condition. Okay, so here I think from this figure you understood what is the race around condition. As long as the clock is high, the output will toggle a number of times. That is, when j and k are equal to 1, initially assume that this q is 1 and q bar is 0. So that whenever we are feeding back that input here and here, this becomes 0 and 1. Then again assume that the clock is high by that time, again it will be again giving feedback to the system. So it will again go to 1 and 0. Again assume clock is high, clock has not gone to the level 0. So that output will again feedback and it will again toggle. So in this case, it may toggle as many number of times. So we cannot predict how many times it will get toggle and what. But what we are expecting is within a clock cycle, it should toggle only once. Output should change only one time. That is what we are expecting. But that is not the case with the JK flip flop. It may toggle, it may change from 1 to 0 or 0 to 1 continuously. Uncontrollably it will get changed. So that condition we need to avoid. So what is the main problem with this? Why it has happened so? Why it happens so? So that depends upon the delay in this particular network. So assume that the clock duration is 5 seconds. For your example, for better understanding I tell you. So 5 seconds is the clock duration. Okay, 5 seconds is the clock duration. Assume, and this delay in this network is 1 second. Assume that the delay in this network is in this particular circuitry is 1 second. Okay, so what happens? After 1 second, whatever input I have given, that will be calculated. I will get an output after 1 second. So that output will come here. Okay, then what happens next? Clock is 5 seconds only. But we got after 1 second I am getting the output. So whenever I am getting that output, again that output will be given back to the system. So that will give the next output. Next 1 second. So this is 1 second, this is 1 second, this is another 1 second, this is 1 second, this is so 5 times. If the delay in the system is 1 second, within this clock, 5 times this output will get changed. Okay, so that is not allowed in case of a sequential circuit. So what we have to do is we have to make sure that output will change only once within a clock cycle. Within a clock cycle, you can change the output only once. So for that, the solution is there are two different solutions. What we can do is we can make this clock cycle as 1 second duration. That is one solution. So every clock you can make it as 1 second duration. Since the clock duration is high, it is changing or it is toggling uncontrollably, right? So what we can do is we can reduce the clock size to a minimum value. That is depending upon the delay in the circuitry, we can regulate the clock. But that is not a practical solution for this particular problem. So what we are doing is we are going for a different circuitry, different sequential circuitry. In that circuitry, we can ensure that the output will change only once within a clock cycle. So that particular circuitry is a master slave JK flip. Okay, so that we see now.